In this tutorial, we're going to have a look at Gauss's law and what it means. Now, Gauss's law allows you to find the flux across a closed surface. So let's give a definite example of this. Say we've got a closed surface, and in the center, or anywhere inside, we've got a charge of plus Q. Now, the electric field lines from that are going to come out evenly in all directions. Now, and the flux is the amount of field lines crossing that surface, or the rate at which those field lines cross the surface. Now, we can work this out by defining a small unit of area on the surface and calling that dA. So that's going to give us a small area on the surface of our Gaussian surface. Now it's important to note the surface can be any shape. I've drawn it as a sphere for simplicity. But because it is an integral, we take an integral, we can work with any shape. It's just a lot simpler with a sphere. Now, what we can say is the electric flux, which is given by the capital Greek letter phi, or the starfighter symbol. Even with the equal sign, it makes it even look more like a starfighter fight. I love that. But it's the electric field, so we can do a sub E just to make that clear. And that's going to equal the integral over the closed surface of the electric field dot producted or dot dA. Now, the electric field is constant, so that makes our life an awful lot simpler, in that what we can do is we can say the flux is equal to the electric field times by the integral of dA. Now, in this case, so that's just going to give us E A. Okay, now the area of a sphere is 4 pi r squared, so we get 4 pi r squared. Let's just write our r in here because it's the radius from the center of the, not from the charge, okay, but from the center of the sphere to the surface itself. Okay, now the electric field is Q. Sorry, that is A. So now the electric field equals Q over 4 pi epsilon naught r squared. So now we can do quite a lot of nice simplifying. Go for a different color. So it's going to be the flux over a closed surface is equal to 4 pi r squared over 4 pi r squared epsilon naught. Sorry, Q at the top as well. And that's going to cancel nicely, so then we just get the flux being equal to the charge enclosed over epsilon naught. And then from this, we can work out some quite nice things, because then if I rewrite this, the integral of E dot dA is equal to Q enclosed over epsilon naught, and we can use this to do some quite nice things, including finding the electric field from, if we know the charge and the area, we can find the electric field. So just to show that a bit more explicitly, let's let's take an example. Go for a new page. If we draw out, say we've got a charge on the surface of a sphere. Okay, so we've got a charge on the surface of a sphere. And it's got charge Q. Now, if we take a Gaussian surface, and the definition of a Gaussian surface is it's an arbitrarily defined surface. Okay, it's an imaginary surface as well, but it can be used to help with calculations. So say if we take a Gaussian surface inside this charge Q, so we want to find the electric field. So if we write out our formula that we found again, which was the integral of E dot dA equals the charge enclosed over epsilon naught. Now epsilon naught is just a constant in this case. It's a value you can find online, and if you need this in exams, it will be given to you on a formula sheet, so you don't need to remember it. It's just a constant. If we just do this real quick, given the fact it's uniform sphere, we can say EA, mustn't forget the vectors, equals Q enclosed over epsilon naught. In order to find the electric field, so we divide by the area, we get the electric field equals Q enclosed over epsilon naught 4 pi r squared. Now, let us just write a few more things on our diagram here. If we call this radius 1, and if we call this just the radius, we find there's a charge outside, or we're looking at our Gaussian surface inside the red one. We find there's no charge inside, so there's no charge enclosed, which means we get the electric field being equal to 0 over epsilon naught 4 pi r squared, which means our electric field equals 0. Okay, so now if we take another Gaussian surface, this time outside our charge, and define this as radius 2, if we just put a few little subscripts in here just to show that. In fact, I'll keep it the same color, that'll probably be a bit simpler. So this time the electric field is equal to the charge enclosed over epsilon naught 4 pi r, in this case r2 squared. Now this time it's going to have an electric field because there is a charge inside, so that's going to equal Q over epsilon naught 4 pi r squared. So as you can see, it is dependent on the charge inside a Gaussian surface. It doesn't matter what's outside, it's only what's inside. Now, if we take a look at this slightly graphically, so say we draw a graph of radius against electric field, and let's say this is radius, the radius of our charge, then we find we get a relationship looking something like this. Now this curve is proportional to 1 over r squared, hence the inverse square law, which we see in an awful lot of things in nature, whether it be charge or gravity or anything. An awful lot of things obey the inverse square law. So that's a basic introduction to Gauss's law. I hope you found this useful. If you have, don't forget to hit the like button. And if you've got any questions, leave a comment, and don't forget to subscribe, of course. Thanks for watching.